Hey, everybody. Hey, Tiffany. Hey, Madeline. Hey, Mohammed. Good to see everybody here. I had to make some calls real quick. Woo, busy day when you got to run around real quick. Sorry about the 5-minute delay right there. Tiffany's got some questions to start. Then we're going to do the 1,000-chip trial. Tiffany, thank you so much. Everyone here is so patient. I agree. I appreciate it so much. No one's ever like, where's Brian? Where is Brian? Where is Mubot? Mubot need to wake up. I had to make a quick call to university stuff. Doing some quick job stuff in the background. Thank you to everyone at the University of Tennessee. Had to make a call to one of the offices, and they were super awesome, super helpful, and great communication right there. So shout outs to the people working at UT. And with that, Mubot is awake. Let's go here. The 900 poll worker question. But how's everyone doing? Mohammed saying hey in the chat. 900 poll workers. Getting it started up here quickly. I think I have a different question right here. In a recent poll. That's a different one. In a recent poll we're looking for. Doing good, doing good. I went and grabbed a quick snack. And then I made a call. My snack, my cookie dough snack. It's gone. Those not kind bars, Quest bars. Good stuff. Shouts to Quest. In a recent poll. Ditto, good to see you. Let's hop over here and check this out. In a recent poll. In a recent poll, 800 randomly selected adults, the presidential approval rating was 48%. Is that good? Maybe. Make a 95% confidence roll for the approval rating. So with this question right here, when we make a 95% confidence roll, well, first let me ask you, is this C or Q? I'll start writing the equation. Is this C or Q? Is it categorical or quantitative? We're asking approval rating. Do you approve of the president? C or Q? Is it C or Q? And here's a hint. Is it C or Q? Which of those is this? Is it C or Q? Categorical or quantitative? It's categorical. Hence why I wrote the equation. When you hear Z-score of 95%, what do you think? Z-score of 95%. A little bit of review right here. A Z-score of 95% confidence. And we're not using T's. 95% confidence Z-score, what number jumps into your head? That's all over the screen right there. What number jumps into your head when you hear a Z-score of 95% confidence? Make sure to go to the David M. Lane if you're ever wondering about a Z-score. Tiffany's got it right there, 1.96. If you have that written down, 1.96 Z-score for a 95% confidence. Once again, we're marking the notation as we do this. So we know what the Z-score is. Let's put our notation on the screen as we usually do. Z-score right here is 1.96. That's because 95% confidence. The sample size is 800. The p-hat is 0.48. What is q-hat? Who knows q-hat? I'm going to pause right here while you figure out q-hat and see if you can find q-hat right now. Great job, Tiffany. Excellent work. 100 points in the chat right there. Q-hat is, we'll write that on here, complement of p-hat. Excellent work. Pink. There we go. Let's pull out the calculator and start doing a solve. Remember, we always solve for the standard error first. Oh, wait. What did I do? What did I do? Why did I write an extra Z right there? Don't know what I'm doing. It's Z is 1.96 right there. I think I was just copying part of the equation. And so we solve 0.48 times 0.52. That's a 5. And then we divide by 800. And then we square root. That is the standard error right there. This is the standard error. Timesing it by the Z-score gives us the margin of error. So that's the margin of error. And then we get the following. So let's write that right here. That is 0.0346. And great work working on this chapter right here. 0.48 plus or minus 0.0346. And that's the margin of error. So let's go ahead and start punching into the calculator right here. We've got 0.48 plus, wait, where are we at? 0.48 plus this. Invalid input, of course, plus 0.0346. There's the upper part of the interval. and to 3 decimals is going to be this. And now we do 0.48 minus 0.0346, and that'll round to 0.445. And so they're asking, do you think the null hypothesis of 48% is true? Now, I'm asking in a different way than what they say. Do you think 48% could be true? Are they testing based on the confidence interval? Test the null hypothesis at 40%. They picked the value at the center of the interval. So do you think 48% could be true if you see 48% in your sample? And here's the values. You do think it's true. So 48% is what you currently believe is a null hypothesis. Do you reject 48% or do you not reject 48? Would you say to me, Brian, I reject 48% as the truth, or I do not reject that as the truth? So which of those would you say to me about 48%? It's in your interval. It's at the very center of your interval. I would not reject it. That's what not reject, fail to reject means. Like, it just means you don't do that. Great job right there, everybody. Madeline, amazing points, Madeline, competing for the top right there. We should get it 100%. I think Madeline was asking about the 1,000 cookie, 1,000 chip trial question, right? Is that the one? I think we have that one lined up next. Let's go check it out. Huge shout out to everybody asking those questions. We've got a few from earlier office hours today. Remind me of them if I forget. But we're going to put those in the video here for everyone who's asking those questions. But we pretty much were close to open questions. So 1,000 chip trial, I think, is one. So we have that one, the 1,000 chip trial. 1,000 chips. Let's go find it. 1,000 chip trial here. It is actually cold in Texas. I heard around Kingsport, Knoxville area was in the 40s. That is insane. How can it be in the 40s? Oh yeah, it's November. Talk about February last year. We were in the teens here in Texas. That was some cold weather. Here we are with some 1,000. It's freezing. Go. Yeah, I got a blanket right now. Got a blanket right here. Nice and keeping warm. Turn on the heat again. So with this right here, I should put on socks. I don't know. I just like t-shirt weather, but it's not t-shirt weather anymore. It's cold weather. So let's check out the 1,000 chip trial right here. Go at your own risk. I gotta play my Pokemon Go. Gotta go catch my Pikachu. That's one of those Pokemon, right? Kidding. I'm a huge nerd. Let's go check out the 1,000 chip trial here on Stat 201. 1,000 chip trial. So what you're gonna do is you're gonna open up a bag of 10 different bags of cookies. You're gonna dump out that bag of cookies and you're gonna count every chocolate chip in those cookies. It's a lot of counting. Someone's got too much time on their hands right here. Condition 1, you want those bags of chocolate chip cookies to be random. Condition 2, these bags of chocolate chip cookies need to be less than 10% of all chocolate chip cookie bags that there are. And condition 3, the distribution of the chocolate chips in the chocolate chip cookie bags need to be nearly normal. Nearly normal / condition. They state the conditions here are a bit weird. We like to do condition 1. Yes, let's do that next, Tiffany. You got it. So condition 1, is it random? Sure. So check the independence. It has nothing to do with 10%. So since they are random, we could assume they're independents. They like to combine those. This one right here, there's actually a quick solve for this. I'll mention the quick solve and then I'll actually solve it. The quick solve for this is the correct scale right here goes from about 900 to 1600. So the quick solve here is it is normally distributed, which means we're going to pretty much meet the nearly normal. But please do this. This is going to help with later. Copy the data to the clipboard. Once you do that, hit Command or Control C to copy the data. And now we're going to go over to Jump. Inside of Jump, we'll open up a new data sheet with File, New Data Table. File, New Data Table. With File, New Data Table, you're going to go to Edit and only paste. The reason we're only pasting right here is because there are not column names. If you paste with column names, you will get a column name at the top of one of the numbers, which you don't want. So make sure it says column 1 right there by just going to Edit, Paste. And once you edit paste, you will see the chips in the cookies going like this. So make sure it's also blue, which you should have. So we can do the distribution by going to Analyze Distribution, and we will get to see the graphic on B right here. Let's just show what B looks like. And under Analyze Distribution, it starts at 900 and goes to 1600. We're going to double click the Y variable of interest and just put that right there. we'll click the top red arrow and then go to stack. And once we have it stacked right here, we're going to double click the axis. And this is all just to make it look pretty right here. And now we go to units of 100. It goes by units of 100. And check, guess what? There you go. So remember, bin widths control how these look. So you could change the bin widths theoretically, and it could look drastically different. Changing the bin widths is going to change how it looks, but it's still the same data. It's still the same. Rock?
It doesn't matter.
He knows about those bin widths. It doesn't matter how the bin widths look. It's all about the same data, just put into different amounts of bins. And so it can look different, but this is the answer right here. It goes from 900 to 1600. The lowest value is only this right here, but did they put them in order? They put them in order? Oh, they almost put them in order. Almost. Almost. So the histogram right here is pretty unimodal, is pretty symmetric. So it's roughly unimodal, roughly symmetric, with no real outliers. So one can assume the data comes from a population that follows the normal, and we are using, we're using the T. Almost caught me off guard right there. The T is when we are doing means. We are analyzing the mean right here, so we want to analyze using the T distribution. So the student T distribution, remember, Mr. T is mean if you're using drugs. So this is the student T distribution to analyze means. The 95% confidence interval for the mean seems like it would take a long time till we realize JUMP has already done all this work for us. One of the great reasons I love this question, JUMP's already analyzed and ran a 95% confidence interval. If you want something other than hints for the visualization, then a 95% confidence interval, you can always choose a different level with other than the ones supplied to you. And this will produce other confidence intervals and put them over here to the side. We get our 95% confidence interval by default, and we have 13.038.33. I think this is the one I got wrong where I put an extra decimal a few days ago. 13.08.3, and the upper bound on it being 1158 point, and that's going to round to 1. Am I reversing the upper and the lower again? Am I? I think I am. That is the lower. 13. That should be right. Do not reverse the upper and the lower. Don't be like Brian. Get them correct. Now, this one's pretty interesting because remember, there are some bags that don't have a ton of chips in them. But what is our interval trying to estimate? It's trying to estimate the true average number of chips. We were working on some visualizations earlier. So when you do the interpretations, I am 95% confident the true mean number of chips in these bags is contained in the interval blank to blank. So this is about the true mean. Because the confidence interval is entirely above 1,000, the number of chips, no, that doesn't mean every bag. No. Because the interval is entirely above 1,000, the mean number of chips per bag is most likely more than 1,000. We have good evidence that the mean number of chips in a bag is more than 1,000. However, an individual bag might have fewer than 1,000. So it's possible that an individual bag could have fewer than 1,000, but we have good evidence that on average, our bags have more than 1,000 chips. So it shouldn't be 1,000 chip in a bag. It should be, on average, we have 1,000 chips in the bag. We can't promise every bag will have 1,000 chips, but if you repeatedly buy bags, you would observe more than 1,000. Oh my gosh, what have we done? Really? Wait a minute. Unimodal symmetric with no outliers. Please tell me you got that one wrong. Brian needs more coffee. Might need to look in this one. This is using the T. I need to talk to my Pearson about that. Because if you don't use the T, because we can do it not using the T, my Pearson, what have you done? I got this one right yesterday. If you went in here and you did not use the T, first time I've had a major disagreement here. If we say use sigma, known sigma, we would enter in this right here. Now the T distribution is part of the normal. And this interval right here, I do not think it will accept. 11.68. If you notice, it's smaller. You're always going to get a small interval with the z interval. So this is using a z interval, and I don't do what Brian did right there. That's a z interval. For the mean, we use t distribution. And let me double check what they said right here. Someone might have been like checking this question and might have changed it because I swear in previous, I might look at my old videos. Well, we'll check that out here on Stat 201. That's the first mistake that I'm like not happy about in a while. No, let's go back here to the main screen. Somebody got that wrong following the video and they're like, no. Sorry about that. It doesn't have outliers. I guess it's important that we say it doesn't have outliers. They really need to combine those two sentences to like, it follows the T. You're welcome, Catherine. You're welcome. Make sure to not make that error I made. It's the wording ones where my Pearson can sometimes... Who wrote this question on my Pearson? It wasn't me. Let's go over. Tiffany has a question right here. Which of the following are true using an alpha level? So we're going to learn what an alpha level is right here. And thank you so much, Catherine. Someone's be like, do you even know this? I swear I know it. T distribution, use it on when we don't know sigma right there. Thanks for it. So it says the normal, but it is, yeah, so choose the one that says the normal that says, make sure to pick the one I picked. If you get it wrong, just email me and say, hey, Brian, this is the one you missed. I got it wrong. So one of the great things about watching Office Hours now is if you hear that and you're like, well, Brian's saying if we got this wrong, just email him and say, hey, Brian, you told me to email if I got this one wrong. Just change it. I don't like things. Yep. I'm watching the chat down here. I don't like ones that, I don't know, are not clear. Sometimes there's not perfect questions. There's good questions. Because some questions are oddly worded. I do like this one a lot. I know which one Tiffany has this about to do. It's the whole thing about whether... It's a really good theory question and helps you understand how we use alpha. This is a very good one. Not that the last one was bad. Was it 16 or 17, Tiffany? I think it's 16, right? I went to 15 instead. I said, is it 16? Yeah, chapter 16. I was in 15. This is all about those alpha levels and when we reject the null or fail to reject the null and how alpha levels impact that. Yes, here it is. Let's go check it out. So what we have here is the different levels of alpha. Now, alpha is what? How would we define alpha? Alpha is basically a bar, and if we are under alpha, we reject the null. So if the p-value is less than alpha, you reject the null. So make sure you know that. Let's put that as a note right here. Take some notes along with us. P-value less than alpha, reject the null. So that is exactly what we do. A p-value less than alpha, we reject the null. Alpha is assumed to be 0.05 by default. That means like you just start out assuming that it's 0.05 unless told otherwise. We will specify alpha by saying, you can tell someone in alpha by saying this right here. You'll say alpha, which is this little thing right here, is equal to like 0.01. So now someone is specifying a different alpha to use. These are the important sort of things we should know about alpha. We're just going to look at it and say, is our p-value below alpha? And if the p-value is less than alpha, we will reject the null. When the p-value is higher than alpha, when the p-value is alpha or higher technically, fail to reject null. Okay, now that we have some good notes on alpha here, let's take a look at what's going on. This question states that using an alpha of 0.05, a p-value of 0.03 results in rejecting the null. Let's put this down here on the bottom of the screen. Tiffany, how does this sound to you that if you use an alpha, I'm trying to get it all on the screen one time. If you use an alpha of 0.05, a p-value of 0.03 would result in rejecting the null. How's that look to you? Using an alpha of 0.05, a p-value of 0.03 would result in rejecting the null. How's that sound to you right there? So if you use an alpha of 0.05, you get a p-value of 0.03, would that result in rejecting the null? Using an alpha of 0.05. That's exactly, because this goes by if the p-value is less than alpha, we reject the null. Does that make sense? If the p-value is less than alpha, we reject the null. And let's go right here. This statement is very, very true because the p-value is less than alpha. Next thing says the alpha level depends on the sample size. Do you see that anywhere on here? Does anything on here say an alpha level depends on sample size? Now we might get into power. No, we don't get into power. Good. So no, nothing dealing with sample. You just say your alpha. Tiffany, say a number between 0 and 1, and you'd be stating an alpha. You can just pick your alpha. You don't usually just pick a random number. You don't usually pick crazy numbers, but we could. You could theoretically just choose any alpha you want. Like, watch this. In the chat right now, I'm going to say alpha is equal to 0.20. I'm raising the alpha. And if I get a p-value below this, boom, Tiffany picked a super high alpha of 0.70, which is totally fine. 100 points in the chat. You just picked alpha. Did you have to ask about sample size? No sample size asked for. You just specified your alpha. So this statement is false. It's not always 0.05. We can choose different ones. It's set independently, does not depend on sample size. That sounds right. Sample size does not depend on alpha either. They're just how much did we sample and when are we going to reject the null. With an alpha of 0.01, a p-value of 0.08 results in rejecting the null. If your p-value was 0.08 and your alpha was 0.01, so a p-value what? You would do what right here? If your alpha level is 0.01, you get a p-value of 0.08, what would you do? So use the tips at the top. If your alpha level, which is your bar, is 0.01 and your p-value is 0.08, what would you decide to do? We would decide to do what? Remember, alpha is the point at which we reject, and we saw a p-value of 0.08, so we're above or higher than that bar. So since our p-value is above alpha, fail because you great job, Tiffany, right there. Remember, just let it fly. P-value is high, just let it fly. And that's what we mean by high p-value. When I say the p-value is higher than alpha is what I'm saying. So catching the lingo right there. Great job. So this statement is false because only a p-value less than alpha results in rejecting the null. Either reject the null or don't reject the null. Speaking of rejecting or only rejecting the null, an alpha level of 0.05 and a p-value of 0.07 means the null is true. What would we do? If we have a p-value above alpha, we would fail to reject the null. So this doesn't mean the null is true. This means we just don't reject it. We don't ever say the null is true. We just say, well, we don't have evidence to go against this. It's like if Brian says he can run a 6-minute mile and you're like, well, I don't have evidence to go against that. I haven't seen otherwise. I don't believe he can run a 6-minute mile, but I can't prove him wrong. I can't show Brian is wrong right now, so I'm not going to reject that. It's weird the way we talk in statistics sometimes, but we're not saying, I know Brian can run a 6-minute mile. We're saying, I have no evidence to go against Brian running a 6-minute mile. I don't have an alternative. So you could say, I currently believe Brian can run a 6-minute mile till there's evidence otherwise. It's not true that Brian can run a 6-minute mile. It's just that at this current time, the belief is this until we have evidence otherwise. We don't state that the null is true. We just say it's what we currently believe. So this statement is false. Because a p-value greater than alpha only indicates there is not enough evidence to reject the null. That does sound accurate. We're not getting an error. There we go. We don't have enough evidence. If the p-value is high, just let the null fly. Just let it be. We don't have enough evidence to go against the null hypothesis. Really great question, Tiffany. And hopefully this summary up here helps with people understanding what we are trying to understand about alpha levels. And when we say an alpha of this and a p-value of this, what it means. I do want to point out there's only two sayings we ever have with the null. We either say, I reject the null, I have evidence for the alternative, or we say, I do not reject the null, which is fail to reject. I do not have evidence for the alternative. These are the only two things, and not reject means the same as fail. I think it's just easier for people sometimes to understand, like, I do not reject means fail to reject. But I like the knots right there. Can we do that? Yeah, of course. Yeah, let's do that one next. You bet. And so with this right here, these are the only two things you would say. You would say, like, I reject that Brian can run a 6-minute mile. I have evidence that he can't. Or you would say, I fail to reject. I do not reject that Brian can run a 6-minute mile. I do not have evidence for an alternative. Like, I still believe that. And so the weird way statisticians talk right there. Oh, man. We got this. Let's get the next question up and going right here. Next question is, Which of the following is a correct interpretation of a p-value that is not very small? Sounds like the results were probable, likely by random chance. And the p-value, that's such a weird way of saying it. Ma Pearson, what are you doing? Ma Pearson asking questions in a weird way. So put those questions in the chat if you have them. Finding... All right, here we go. We'll do some multiple choice right here in this chapter. Multiple choice, chapter 16. Let's go check out some multiple choice. Here we go. Multiple choice, chapter 16. So, which of the following is the correct interpretation of a p-value that is not very small? So, we're saying the p-value is high, and probably higher than alpha. So, a p-value is a probability. So, if you see a high p-value, would that tell you that what you saw was likely or unlikely? Like here, we can go look at a p-value. Let's go grab a p-value, and there's a bunch of p-values on the screen. Ridiculous p-values. This p-value is very, very tiny. This p-value is pretty bitty big right there. Here's some other p-values. Here's a tiny, tiny p-value, tiny, tiny p-value. Here's a larger p-value. If the p-value is high, what you saw was likely. Does that make sense? So don't worry what all the results mean. These are just all different p-values. And when a p-value is high, it means what you're seeing here is likely. Something likely would be surprising. Like if I tell you it's likely to rain today and you saw it raining, would you be like, or would you be like, I expected that. So something that is likely, because remember the p-value here is high. So this is a high p-value. We'd fail to reject the null, correct? And you would say that it's what? Would you say it's a rare event, or would you say it's not surprising? If something's likely to occur, i.e. a high p-value, I wish it just said a p-value that's high, because it's saying not small. So a high p-value would be something not surprising, because it's likely to occur, or it'd be a rare event. It'd be not surprising. And if something's not surprising given the null is true, you would not reject the null. So what we're saying here is, what we saw was likely given the null is true. I'm not surprised. Like, if the null is true, what I'm seeing here is very likely, so I'm not surprised by this, so I'm going to still believe the null. So, good question right there. I wish they just said high p-value, because not small means high p-value. What they're trying to say is a p-value above alpha. More multiple choice questions. If the p-value is smaller than level of significance, which is alpha, what conclusion? This one's really quick, A, B, C, D. P-value here is low, what do? P-value is low, we do what? You know it. A, B, C, D. P-value is low, what do? Now, there's only two answers on the screen that work. We either reject the null or fail to reject the null. P-value is low, do what to the null? Ah, I think we'll get to that one, Tiffany. I think we're going to do that one. You got it. The p-value is low, do what to the null? P-value is low, reject the null. P-value is high, just let it fly. Just let it be. Don't reject it. Fail to reject. So because the p-value is lower than the level of significance, we reject the null. Oh, you getting. Yep, might tell it next right here now. What is the name for that threshold thing? Remember we talked about a threshold thing a moment ago? I promise we'll get to this one, Tiffany, that you have. What is the name for that threshold thing I talked about that is the point at which we reject? Like we could say we set the bar here, and whatever we say, this is like our standard, that if it's lower than... Oh, yeah. No, we will be doing that one. So what is the threshold? The bar at which we set, and this is a good like flashcard thing, the bar at which we reject the null hypothesis is going to be the what? The threshold bar by which we specify the point at which we reject. And it is 0.05 by default. And so what is that 0.05 thing by default that we have? Like by default, this is 0.05 unless someone states otherwise. So unless stated otherwise, we assume 0.05 is this value. And this value, this threshold thing is called the what level. It's the level of significance at which we would reject. Assumed to be 0.05 unless stated otherwise. So if it's less than this value, then we will reject the null. And it's assumed to be 0.05, and we can specify it by saying this is equal to this. This whole thing is called what? The bar at which we reject or not reject. That bar we set is called the what level. Level of significance, but also called the what? Oh, I'm on Top Chat. I hate you, Top Chat. So what do we call it? What is it called? It's called this symbol too. So what do we call it? The bar at which we set it. Not mu. Alpha. Alpha. Good guess right there. Good guess. It's called alpha. It's called alpha. I resumed the screen. It's called alpha. The alpha level. So the level of significance, the alpha level right here, is the bar at which we set it. And that's the point at which we reject or fail to reject the null is the alpha level. I think we'll be getting to yours here in a second. What is the probability that the test correctly rejects the false null? Now, this gets into your questions here, Tiffany. Tiffany was asking, what is the probability that the test correctly rejects? This is it. This is the one. I'm easy to trick. This is the one you're doing right here, and this one is a little bit tricky. Let's bring up the notes right here and review something that we will be going over in class. This goes over the idea of power. So the idea of power is not making a type 2 error. We'll be going this over more in class, but we have here, don't do it that way, I do it this way. We have here A, B, 1, 2, positive, minus. So you'll hear me ask these questions in class, like how do we count? How do we do letters? My way of teaching it. So we have what's called a type 1 error. And a type 1 error is associated with alpha. A type 2 error is associated with beta. A type 2, most commonly, but not always, I think of as a false negative. Like if you go to the doctor and you run a test and they say you're fine, but you go home and you're actually sick, that's a false negative. That would be a type 2 error, hence type 2 with the negative. And then we have down here a type 1 error, which is a false positive. You go to the doctor and they say you're sick, but you're not. False positive. That is a type 1 error associated with your alpha level. So we might be wondering, well, what is this whole power thing? Well, if you go to the doctor, they want to be able to figure out you're sick, right? They don't want false negatives. So power is the ability to basically find people who are sick. Like a powerful test would find out everybody is sick. So when you think about this, power is actually not making type 2 errors. So power is the formula 1 minus beta. So power is not making type 2 errors, which power is the ability to correctly reject the false null. Because if the null is false, we should not make a type 2 error. A type 2 error is when we fail to reject the false null. And I want you to hear something real quick. And I'm going to teach 2 more seconds on this. In a type 1, the null is true. What letter am I holding up right now? In a type 1, the null is true. You got a cheat sheet right here for the test. What letter am I holding up? In a type 1, the null is true. In a type 1, the null is true. So what letter is this? Well, this is the 1, and then this is the what? In a type 1, the null is true, and it would be a mistake to reject it. This is a T, right? Great job, Tiffany, right there. And in a type 2, what do you think the null is in a type 2? In a type 2, the null is what? What do you think this stands for? I'm going to say in type 1, the null is true, and we reject it. In a type 2, the null is what? If we make a type 2 error, the null would be false, and we fail to reject it. A student made this up so long ago, and everyone who's practiced it has been like, that's the easiest way to keep them straight. In a type 1, the null is true, and we reject it. In a type 2, the null is false, and we fail to reject it. Remember, you do it twice right there for the type 2. The null is false, and we fail to reject it. Because that's an error. If the null is false, we should reject it. So a type 2 is when we have a false null, and we fail to reject it. These are F's right here with the type 2. Probably one of the best ways to ever memorize these things with what they are. So power is the ability to correctly reject a false null. Literally the definition right here on the screen of what is the probability that a test correctly rejects the false null. And this is what we want. To correctly reject the false null is to not make a type 2 error. So it's actually the complement of type 2 error, which is power of a test. Significance of a test is the alpha level, and p-value is unrelated to these topics. But I mean, it's connected tangentially, but not completely related to the idea of all this. Really good question there. That's a good one, understanding the topics. What type of error is made when a false null is not rejected? So I want 2 or 1. Now be very careful, Tiffany. These questions are almost 50-50 guesses to people. But remember, type 1 null is true, we reject it. Type 2 null is false, we fail to reject it. So which one is this? Is this a 2 or a 1? And then we'll review. So it says, what error is made when a false null is not rejected? So is that a type 1 or type 2? And then just read. Type 1 null is true, we reject it. Type 2 null is false, we fail to reject it. So this is type 1 or type 2 error? Good practice for the test. I swear on the test, these are like 50-50 guesses to people. And I'm like, no, did anyone learn it? It's all right if you get it wrong. It's all right. Yes! Yes! Thank you. I needed that. Exactly, because it says the null is false and then not reject is fail to reject, right? So it says not reject. It's not saying fail to reject, but the null is false and we fail to reject it, which is not reject. I swear, you'll see in class, I'll about lose my mind. But these are almost like 50-50 guesses when we get to the test. And I'm like, oh no. Take a look at it. Yeah, we can take a look at it here. Jake, good to see you here. If you have questions, let me know. Let's go look at the next question right here. What error is made when a true null hypothesis is rejected? In a type 1, the null is true and we reject it. So that's the other type of error we can make. So we got the other side of it right here. When the type 1, the null is true and we reject it. Here, I'll go look at the other screen right here. I think that might be it for the multiple choice. That's got all the multiple choice done. So if you have a question, put those questions in the chat and we'll take a look. Let's hop back here to the main screen. Tiffany, I'll go take a look at that. Excellent work, everybody. So have those questions, put them in the chat. And let's go take a look. You're wondering about, so I got something wrong. Number 4 on my quiz. Can you take a look at it? Yep. Let me go take a look. Got a jump thing over here. Number 4 on the quiz. Let me go find this real quick, Tiffany. Excellent work. Practice those concepts. We'll get them down. Some memorization, but we don't want to just memorize. We want to make sure we have it down, like we understand conceptually. And that's when you really know it. Well, let's find out. Oh! Double check. You got it, Tiffany. I have faith. You got this. You got it. You're going to have to take another attempt, but you got it. I believe in you. You got this. I think you can see it too. Which one do you want? Mama wants one right here. Let's see. Can we look at D and E on the 475? Mm-hmm. Yours might be different than mine, though. Is there any way you could go over number 2 on the chapter? Yeah, Juliet, of course. Of course, Juliet. Thank you for being here, Juliet. Let's do it here. I think we're going to do, I think Mohammed has the next question. Then we'll do Juliet's question. D and E, is it part, which one? Question 1, Mohammed? You bet, Juliet. Let me move this little screen right here. Is it question 1, Mohammed, or question 2? And great work. You got this, Tiffany. You got this. Remember, the questions can change because sometimes the value is in the interval or sometimes it's not in the interval. So they do change the way the questions work a little bit. Part 1, awesome. Let's go take a look at this here. So they will change the way the questions are a little bit. They will change them. Part D and part E. We'll try to do some different models right here. I think we did the Hilo last time. Let's go take a look at this right here, and we will pipe in, do some predictions right here. So did we make a video on the predictions? Trying to think. And then we need to plot it. What does this say? Which model? Just summarize 2 hands. Yeah. Let's take a look right here. Okay. Let's take a look. I was thinking these are on the book, but it is not working for some reason. I keep using the forecast model without the prediction intervals. Or when you're trying to plot it, are you trying to plot it, Mohammed? Is it your plot is not working? Here, we'll pause here for a second. Because I try to do things that are a little bit different on these. Is your plot not working? Like, is the plot not plotting? Like, is it giving you the predictions, but it's just not plotting it? Which, we should get the prediction intervals. You should get the prediction interval tables. So I don't want to quite do the whole thing. I'm trying to figure out a way to not do the whole thing, but give prediction intervals. Yeah, we should get the prediction intervals. Let me go grab some code right here. We'll do something similar. We'll do like a similar model. So let me take a second right here, and then we'll do some more 201. Okay. So we need to make some scenarios right here. I'm going to get some code up and going. Similar but different models. And we make some new data. And let's make some models right here. I'm getting some models ready to go. we could predict. It was all temp. You know what? Let me pull up the. Well, it'll take a while. Getting the whole data frame going because I don't want to use the same data. Trying to get data going, Mohammed, without showing the answers. This is what it's showing for the 80% control. It's not showing any of the values. So you should have, talking about the Hilo right here, so I might try to do this like off screen. You're piping in, do you have your forecast saved? Did you forecast the new data? Mohammed, when you run, let me run this code right here. 2 seconds. I'm just going to ask questions mainly. When you run, get the code up and going. Okay, there's the January. When you take a look at your forecast, what shows up for your forecast? So what is appearing for your forecast right now? Here, let's go to the main screen. So we should see our forecast. And let's go look at the forecast right here. And let's go check this out. Okay. So with our forecast right here, and here's how we can layer everything together. Got a separate model over here. So when you make your forecast right here, we get the forecast and always look at what you create right here. We're running the fit through the forecast for the new days. We can see right here the different forecasts we're getting, but we don't have the intervals yet. Double check, Tiffany, double check. You got it, you got it, you got it. Put it in the chat if you remember, Tiffany, and I'll double check right there. Remember that threshold we keep talking about, or that threshold we keep talking about when we reject or don't reject. So with this right here, we have it. Let's go ahead and take a look at this. Here we go, and it is making the intervals. So you should get the following plots. And now we want to take our forecast, and we want to pipe it through the Hilo, which is going to get us our intervals, used to extract a specified prediction interval at a particular confidence level from a distribution. So we're going to get this right here. I think we need to add one more thing, which we can do. But now when we go, we can take out of here, and we can go to select minus, and let's move out that model stuff right there. Oh no! Really? Oh, is it dot? It's dot model. Really? Dot model. So that moves out the model right there, I guess. That's good right there. And so now there's the prediction intervals. Yeah, definitely location. We can do the yoga problem. You bet. So right here. Does this, what are you getting, when you look at your forecast, Mohammed, are you getting the following? That's the wrong forecast. Are you getting the following? These are naive models I was making over here. Are you getting the following forecast? Like, does this, yes or no, this is what you're getting for your forecast? Does that look like your forecast right there? Does that look like your forecast? Yep, so that looks like your forecast, right? And then you should be getting, you know, we're predicting, well, we haven't gotten the demand yet. So now when we run right here, we got our forecast saved, and then we can plot the different forecasts right here, which we already have on the right. And then you should be able to take the forecast, and you don't have to do the next step, but we want to pipe it through, well, we want to do this step. We want to pipe it through the Hilo, which is going to extract the intervals. Now the reason you could go, and truthfully, life would be easier if we just go right here. Is that it? There's the 80%. So what's the name of the column? Is quote 80. Let's see if that'll let us just grab it right here. Oh, we lost our parentheses. 80% not found. Really? It won't let me select that? Well, we're going to find a way to select that. Oh, what am I doing? Everyone should see that error right there. I didn't use the select. I'm going to go to select and put the 80% in there. And there we go. This is probably the best way to do it in my mind. So where do you think the error is? Hopefully this is showing it. Because if you have the forecast right here, you should be able to run it through Hilo and get the predictions out of it. Does that make sense? So we are able to get these forecasts right here. Could probably go It looks to be everything. Think of how to narrow it down further. Let's do that. Good. And there's our two intervals. So there's the two intervals right there for the low and the high. Just depends on how you want to report them, but these are the two intervals right here. Does that make sense? There's the two intervals, and you can see them behind my head right here. It's reporting 80% confidence intervals, so it's doing the smaller one. With Hilo, we should be able to change it. I wouldn't suggest. Still not showing the 80% interval when I run. But what happens when you run? Try doing it with... Try saving it into predictions. Try saving it right here. And then take a look at predictions. Ooh, what? What? What the heck? Oh, wow. I've never seen that. That's interesting. That was funny. Not funny. Wow, you can't do that? That's weird. So you should be able to... We won't put a select on here. What's mad? Oh, it's trying to pipe into there. Wow, you can't do that. And look, do you see it? You can see the names of the columns right here. Should go over the link. Yep. So with this right here, we have 80% and 95%. I don't know why it doesn't show it. It's something weird about the way R likes to show this. But here's the 80% and here's the 90%. So if you wanted, probably it'd be better if we went to the select. If we did select 80%, 90%, and that doesn't exist. How's it spelled again? All those errors. Gotta love those errors. It's saying this is a variable that exists right here. Oh. All the errors. It's weird that it takes it certain ways. Yeah, we did some chapter, we did the chapter earlier. We'll be doing some more here in a second. That's so interesting. Can we get the 95% also this way? Put it next. And there we go right there. There's in the order right there. So here's the two intervals. And once again, the two intervals are being shown right here. So you can see the two intervals for the cold and the hot day. How's this looking, Mohammed? Try using the select right there. You might need to copy it. Here, I'll drop this in the chat. But that's the way it looks. I think it's got the back ticks. So just doing that right there. It's the alpha level. The alpha is the point at which we reject the null hypothesis. It's the threshold bar at which we reject the null hypothesis. I think you might have had the back ticks in there weird, Mohammed. Like, so the way I have it, because it's not like a quote, it's a backtick. What type of error is made when a true null hypothesis is rejected? So if the null is true and we reject it, the null is true and we reject it. The null is true and we reject it. Practice. Let's go check out the next question right here. Hopping back to the main screen. Next question is, let's see. Number 2 on chapter 14 homework. Thank you so much, Julia, right there. Number 2 on chapter 14 homework. Number 2, chapter 14 homework. You're on the right track, Tiffany. Great job. Just remember, the null is true when we reject it. That's the answer right there. If the null is false when we fail to reject it. Number 2, chapter 14 homework. Hot dog problem. Well, let's get started here on the hot dog problem. Great job. Awesome. Let's do this. Chapter 14, hot dog problem, homework. Okay. So what's the first thing we're going to do right here? Everyone should know, what are we going to do when we get to a problem like this? We see a problem like this, we think to ourselves, notation. So the notation is the key to solving a lot of these problems. Please identify for me as much as you can in this notation. What do you see up there that you could tell me about? This will help with the formula. N is 50. Alicia, great job right there. Do you see anything else? Keep going, keep going. What else do we see? S is 37. Excellent work. 100 points. Haven't gotten points lately. S is 37. What are the degrees of freedom? For a one sample T, what are the degrees of freedom? Let's pull up the complicated formula. What are the degrees of freedom for that one sample T? We lost our formula. Oh no. Oh, there they are. There's the formulas. Correct, Lakeisha. We're going to go over there to the T-applet here in a moment. Excellent work. You are correct. We'll go to the T-applet to get the 95% confidence T-score. And so what are the degrees of freedom, which tell us which T we are using? So the degrees of freedom, and they're down there. So what are the degrees of freedom going to be? Which that tells us which T we are using. 40, amazing work. Great work. And then we're only missing the mean, which is the sample mean of 302. And the T statistic will have to be looked up via the applet. Go away from my pen for a moment here. And we're going to go over here, close this down for a second, and put in 49 degrees of freedom, because that was our degrees of freedom, and that's actually the answer. I like to do it this way because I graphed the middle 95, and the T statistic is 2.01. 2.01, because this is going to be the T we use for the 95% confidence for 49 degrees of freedom. Make sure you put in your proper degrees of freedom. Your T might not be this. It might be different. It depends on your degrees of freedom. So we hop back over to here, and it was 49, correct? 2.01. So let's write that in right here. And going down to here on the bottom, the Y bar is 302 plus or minus 2.01, which is basically 2. 37 over square root of 50, which is almost 7.07, I think. And now we go back. Calculator time. I might disappear so we can see the calculator. And we do the standard error first. So 50 square root. And then we take 37 divided by 50. And now we're going to times that by 2.01. This is now the margin of error. Remember, if we multiply this all over here, it's the margin of error. And we can rewrite this interval as 302 plus or minus the margin of error. So this is 302 plus or minus that margin of error of 1 or 10.52. And that is the interval. So let's go ahead and write this in here. How did you find the degrees of freedom? Julius, great question. How did we get the degrees of freedom? Who wants to remind everyone, how are we getting the degrees of freedom to be 49? For the one sample T, how do we find degrees of freedom right here? For the one sample T, how do we get the degrees of freedom? So how do we know what the degrees of freedom will be for the one sample T? How do we find that? Great job, Lakeisha. Thank you so much. Good practice right there. I love it. Just everyone helping each other. Vols help vols, and we're here to practice. Thank you so much, Lakeisha, right there. Excellent work. And it is n-1. Sample size was 50. Remember, one sample T, n-1. One sample T, n-1 degrees of freedom. Thank you so much. Another 100 points. Thank you, Juliet, for asking, and thank you, Lakeisha, for answering. So with this right here, yeah, once you see like, oh yeah, you're like, I get it. Yeah, it's good practice. On the test, if something, would you love it if a test question said, what are the degrees of freedom for a one sample T? And you're like, oh, it's just n-1. Look, sure, easy points. If we have it and we know it, we can get it. And so now we're just going to add and subtract this number. I'm going to go over here. So please do. Someone's going to be like, how in the world are we supposed to get degrees of freedom? You say, well, it's just n-1 or n-1 for the one sample T. So they say, oh, no, really? Really? And you're like, yeah. Like, once you know it, that's the answer. If you don't know it, it's really tough. You're like, how do we get that? But no, it's just one of those things. It's like, luckily, a nice and easy formula. Every semester I joke, like, we're about to do a complicated formula. And then people, like, he's messing around with us. I'm just adding and subtracting these numbers. Should be right. Fantastic. Thank you, my Pearson. So kind of you. And now, what have we assumed? Oh, I gotta love these assumptions. Once again, I would not ask these this way on a test. We have assumed that they are independent and they are normal. Yep. Next, Is the randomization condition met? I don't know, but we can assume. Gotta love to assume things. Next, are these less than 10% of all hot dogs? Are these 50 hot dogs less than 10% of all hot dogs that exist? Yes. The 50 hot dogs are less than 10% of all hot dogs. Say we're pretty good there. Next, is the nearly normal condition satisfied? Probably, because we have a pretty large sample. So the pretty large sample would have to be extremely skewed. Just by virtue of knowing the sample size here, we have a sample size of 50. Unless it was ridiculously skewed, we probably wouldn't be good. So we don't know, but since the sample size is 50, we're probably good. So we're probably good because we have a large sample size. So we're passing the nearly normal by way of large enough n. Explain what this means. I am blank % confident. Do remember, I'm going to show the explanation of the interval again. We did it earlier, where we say I am blank % confident that the true blank is contained in the interval blank to blank. So I am 95% confident the true mean sodium content of these hot dogs is contained in the interval 29.15 to 312.5. This one sounds the most like it. They changed the wording a little bit, but we are is I am, and then they're talking about the true mean sodium content of hot dogs is contained in the interval. The interval contains it. And that's close enough to what I say. They just didn't put the numbers. Good question right there. Good practice. Hopefully everyone's acing that question. We're going to hop over and do a few more questions. Let's go check it out. Next question. Let's go and see it. The next question goes to, I think Vincent has one, and then, or Tiffany might have one. Let's see. Was there one before that? Julia had the one. So we'll do Tiffany's question and then Vincent's. Tiffany has a question about, what was it again? Before lending money, banks must decide whether the applicant would pay it back. Let's go check this out. This is dealing with null alternative hypothesis on chapter 16. So we're going to do some nulls and alternatives. Where are my things? Oh my gosh, I need to close some tabs because I'm losing my tabs. Slowly losing my tabs. Here we go, back to my tabs. Chapter 16. Get everything loaded up here. It's Haslam Friday. Haslam Friday. Gotta get my bowl, my cereal. Haslam Friday. Chapter 16 quiz loading up. And hopping over. And we've got the scenarios up. Scroll down here to the bottom. Yeah, the yogurt problem. Yeah, Lakeisha, we gotta do that, right? Did you say, I think you're first. We'll knock this one out because I've already got to load up. And then Lakeisha, yours will be next. Thank you, Lakeisha, for asking about that. Let's do that one next right here. Screenshot the Discord showing the intervals. Yeah, send me your code too. Send me the code with a screenshot. Send me the code and the screenshot, and that'll help me see what's going on with it. Then I can like alter the code and see if it works. Like to see what's happening. Well, there were more multiple choice. Okay, here we go. Before lending money, bank problem, and let's do this right here. So the null hypothesis is what we start out believing. When we have a null hypothesis, we have an initial belief, and if we have evidence, we would reject that belief for something else. So any applicant with a lower point total than a certain cutoff is just denied a loan. Pretty interesting. Before lending money, banks must decide whether the applicant will repay back the loan. One strategy is a point system. Loan officers, so much information. The higher the point total, the more convinced the bank is that it's safe to loan. Okay, so that's evidence to loan them the money. Any applicant with a lower point total than a cutoff is denied a loan. So that'd be, you can't be it. So looking for evidence to loan them. We can think of this as a hypothesis test. Since the bank makes its profits from interest collected on repaying loans, the null is that the applicant will repay the loan. Okay, so they're going to repay a loan to start. And they should get the money. If a person's score falls below the minimum cutoff, the bank will reject the null hypothesis and deny the loan. So we have the null hypothesis right here being, let's write out our null. The null hypothesis is lend money. The alternative is don't lend. So with the null being lend money and the alternative being don't lend, what is a type 1 error? So in a type 1, the null is what? In a type 1, one letter. In a type 1, the null is what? Because I think that's the first one we're asking about. In a type 1, the null is what? In a type 1, the null is true, right? So if we made a type 1 error, let's hear it here. When a person defaults on a loan, what type of error did the bank make? In a type 1, the null is true, but we reject it. So in a type 1, the null is true that we should lend them money, but we reject the null and we don't lend them money. So this is a type 1 error here when the null is true that we should lend them money, but we don't. What type of error is made when the bank misses an opportunity? That sounds just like a type 1 right there. If you heard what I said, the type 1 is when the null is true, but we reject it. So it's true that we should lend them money, but we reject this and say don't lend them money. Where a type 2 error is when the null is false, but we fail to reject it, so we lend them money. So we've made an error right here. The null is false, and we fail to reject it, so we lend them money. So someone does not pay us back because we should not lend them money. The null was false, but we're going to not reject it. So that sounded a lot like that first scenario to me, which is when someone defaults on a loan. That was a type 2 error. So those are complementary to each other. Suppose the bank decides to lower the cutoff to this. Is this analogous to a higher or lower alpha value? So alpha is the ability to reject the false null. And let's think about this. Oh gosh, my brain's breaking on this one. This one's always the one that's a little bit weird right here. So they're going to do what right here? Are they going to reject the null more or less? So they need more evidence to reject the null. And so if they need more evidence to reject the null, because if they lower the cutoff, that would mean they need more evidence. So this would be a what alpha level? Now be careful, I'm saying you need more evidence to reject the null. Would that be a higher or lower alpha if you need more evidence to reject the null? So if you need more evidence to reject the null, would that be a higher or lower alpha? Because alpha is how much evidence we need. So if you need more evidence to reject null, remember the alpha is that bar you have to get under. And if you need more evidence to reject the null, that would be a what alpha level? It'd be lower. It's confusing in that regard because more evidence means you need a lower alpha because your p-value has to be below alpha. So you would need more evidence. So in this instance right here, we're asking for more evidence that somebody is going to default on their loan because we're lowering the bar. Like we're saying like, okay, so we're going to need more evidence to say you won't pay back the loan. Like instead of the cutoff being 250, we go down to 200. So now we'd need even more evidence, which means a lower alpha level. That's a tough one. Tricky. It's caught me off guard before, and this last one has too. What impact does changing the cutoff levels have on the type of each error? So lowering the alpha level is literally the same as decreasing your type 1. And this goes back to what we wrote earlier. I should get this right. Earlier on, we wrote the following. Alpha is 1, beta is 2, plus minus. So we've lowered alpha. So if we lower alpha, what did that do to type 1? I believe so. So if we lower alpha, then what does that do to a type 1? Alpha is the type 1 error. So we will have lowered the type 1 error by lowering alpha. But what have we done to type 2? These are not complements of each other, but alpha and beta are inversely related. So by lowering the type 1 error, or by lowering alpha, we lower the type 1 error. Like alpha is type 1. Like you say, what's your alpha? That's your type 1 error rate. You say, what's your beta? That's your type 2 error rate. But they are not complements to each other. Type 2 will go up. So you will have more people. So think about this. If you are looking for more evidence to reject loans from people, you will make less type 1 errors. Like you will, in more instances, give loans to people. But you'll also make more type 2 errors, which is when you give loans when you shouldn't. So you'll make less type 1 errors where you fail, where you're not rejecting the null and not giving money, which means you don't give money to someone. And then in type 2 is going up where you're going to give more loans where you failed to reject the false null. So you're going to have more problems with people not paying back their loans, which makes sense. Just think about it theoretically. You're going to have more problems with people not paying back their loans, but you're going to get more people to get loans who would pay it back. So the type 1, there's going to be a decrease to the type 1 and an increase. Let me look at what I drew again. Yeah, because alpha is going down. Should be right. Don't break my brain today. Woo. Tricky. Decrease type. Yep, exactly. Because alpha is literally, since we said lower alpha here, that is literally decreased type 1. Like lower alpha is by definition, like that is definitionally decreasing type 1. Alpha is the type 1 error rate, like 1A, 2B. and they are inversely related. They're not complements, but lowering alpha would increase type 2. So if we know that we decreased alpha, like with this being true right here, lower alpha literally means increasing type 2. And lowering alpha literally means type 1 has decreased because alpha is type 1. Good stuff right there. Good question. Tricky question. Just understanding it theoretically is the most important thing right there. But good stuff. Lakeisha had the next question. Let's go check it out. We've got time for these 2 more questions right here. The frozen yogurt question. I found some really good frozen yogurt bars. They're so good. I get a box of them and I go, sometimes I eat like 2 in a night. They're only 90 calories. I mean, how can you not? How can you not be like a 90 calorie frozen yogurt bar? Come on, best thing ever. And they're mint chocolate chip? I'm just really sad right now that I don't have any more of them. I need to go run over to HEB and buy more. They'll be like, you that guy who buys up all our frozen yogurt bars? I say, yep, that's me. They say, thank you. I say, why are you saying thank you? I say, I don't know. Everyone's weird. Best story ever. Frozen yogurt. Here we go. Stat 201. Let's go check it out. Marble City Market opening in Knoxville tomorrow. Check it out. Haven't seen it. Haven't even heard about it. Check out Marble City Market opening in Knoxville. Shout outs to them right there. How would this affect the power of the test? The power of the test will increase. That would be if you were to do that. If the hypothesis test is tested at the 5% significant level instead of the 1, the power of the test would increase because increasing alpha decreases beta, increases power. So you are correct. The power of the test would increase because the level of significance increased. Yep. It's tested at a higher level. We can find more results at a higher alpha level. Haley, good to see you here. Let's go check out frozen yogurt question. So we are with the frozen yogurt question, and we have what kind of data? I want to see C or Q in the chat. The frozen yogurt question right here. Speaking of Marble City, frozen yogurt right there. What do we have right here with C or Q? Is this C or Q? You can see up here the answer. I'm going to go copy the data while you think that over. So we're going to copy the data to the clipboard. What kind of data is this? Here we go. Copy, copy, copy. Who knows for 100 points in the chat? It's kind of nice job, Tiffany. 100 points in the chat. Who knows what kind of data this is? What kind of data are we working with? It is what kind of data? File, new, data table. File, new, data table. And now we put the data in with Control C. We got the data. You will not paste with column names right here. This is not pasted with column names. Now, very important to know whenever you're working with data, we need to know if that data is C or Q. So what am I talking about? Quantitative or categorical? What kind of graphics do you notice over here? Be very careful. A lot of people might say that this is a different type of graphic than it is. Oh no, Sherry. We seem to be doing okay. I'm sorry, Sherry. What kind of data is this over here? Is it C or Q? Yeah, definitely, definitely. Well, I'll be teaching here in a moment. I'll be able to look at it in a bit. You bet, Tiffany. I'll be teaching here in a moment, so you got it. I'll make sure I get you got it. It is Q. Great job. Oh, Lakeisha right there. It is quantitative. Oh no. Hope you're having a good time. It's quantitative, so we make a histogram right here. So let's go to Analyze Distribution, and we're going to double-click the variable. And once we double-click it, we get a histogram, but it's not quite our histogram yet. We're going to click the red arrow right here and go to, or this red arrow, excuse me, and go to Stack. And this will allow us to put it in horizontal layout. With it in horizontal layout, we're going to change it to 80 to 200 by units of 20. So we're going to go right here, double click that. Please tell me to slow down if you need. And there we go. And let's click OK. And look at that. That should give away which answer it is. That should help us know the answer for certain if it's A, B, C, or D. And if you look, you can kind of tell the way the data is. It doesn't have a strong peak in the center. Just by default, the way it looks right here, do you see how it says like 80, 100, 120, 160, or 140, 160, 180? So it's just the way they did it. Great question, Lakeisha, right there. If you double click this, you can change it. It just makes it look like theirs. Yeah, exactly. Great question, great answer. Yep, no, keep asking me like, why do we do that? There's no real reason other than that's the way they drew their graphic, so we can make ours look like theirs. And because the bin widths control very much how these look, you can change the shape of it by changing the bin widths. So if you change the bin widths, it'll look very different. Remember, bin widths control how much data goes into between certain numbers, and now our data looks like theirs. Still looks like it, even though I've maybe made some changes. But the bin widths are arbitrary. Like you could be like, this is still the same data. That's still the same data. It just looks all crazy. But we'll make it look like it again. Okay, that's got it. This is the data. Now, the next one's really tough unless you know some tricks. The trick for the normal probability plot is follows. The normal probability plot shows you the value of the y variable on the left. So if you look right here, you have the values of the y variable. So some of these might actually have the right values, but a normal probability plot, the way we usually draw them, the way they're drawn here, go from the bottom left to the bottom right. So I guess they go from down here to up here. What are the only two answers that seem viable right here? What are the only two possible answers that you see in this output that go from the bottom left to the bottom right for a normal probability plot? And they should follow a linear pattern if they're normal, C and D. So now you might say, well, how would I pick between these? Do you notice right here that the y value is about 120, and then this one is about 180? So these are the values of the frozen yogurt that we're seeing. Sherry, great job. Lakeisha, great job too. Awesome work. So you would say there's a big what in the data, 3-letter word, fall into the what right here. There's a big what between the y values of 120 to almost 180. There's a big what, fall into the what right here. There's a big what in the y values, because these are the y values, and this is what we would see if they're normal for z-scores. Don't worry about that so much. Just look at the y values. There's a big what in the values of y right here. There's a huge fall into the gap. Exactly. Now, if we look over here at the data, you'll see 150, 178, 163, 145. Wait, there's supposed to be a big gap if that exists right here, but there's actually data. So this is the correct one right here because there are the values. That value right there is 178. This value right here looks to be 163 and then 150 and 145, very close to it right there. So this is the right answer. There's not this big gap between the highest value of 178 and then there's no data right here. So that would be more of an outlier if that is the pattern, but no. So the way the normal probability plot should look is it should look fairly linear. And this is not some sort of linearity test. It's testing to see if it's normal. So the straighter it is, the more normal it is. And this one looks pretty normal. Randomization condition is met. We randomly took our frozen yogurts. Obligatory random. The normal probability plot is roughly straight. And the histogram is unimodal and symmetric. And that's mostly unimodal, mostly symmetric. Pretty good right there. And we should be good on that. Let me look at the other one. It's not bimodal. And this one right here says it's not met. Yeah, it's not bimodal. It's not bimodality. Now, the remainder of this question is the really nice part. This is the Christmas gift, the early Christmas gift right here, to where we go and look at our jump output, and guess what we already have created for us. If you didn't get the right interval, like if it asks like a 98%, you could go right here and go to confidence interval and then choose a different one, even other, hints for the project. So if you have to put in another interval, you can change it to like 0.999 and change it to a different type of interval. But you notice right here we have the lower of 114.77. So 114, where'd it go? 114.77. You could, it would be a lot more work. You could do it with the applet, but so you'd have to find the mean of the data, the standard deviation of the data. There's 11 frozen yogurts, so it'd be a T of 10. So here I can show you how it would be solved. Let's go show it in the applet. I wouldn't do this one via the applet. You could for practice. So watch this. With the T applet, good question right there. Good practice. We are building a 95% conf store, right? So we need to go to the applet and we need to get the T with 10 degrees of freedom. So let's go here and get the T with 10 degrees of freedom and 10 degrees of freedom already in there. 95% confidence. And oops, so it's 2.228. And so what you would probably want to do now, if you're solving this by hand and want to practice, you would go and you would take, the answer is already on the screen with the jump output, 2.228, remember that. We got that from the T applet. So what we would do right here is we would take and do y bar plus or minus T with n minus 1 degrees of freedom, S over square root of n. Remember, we already have the standard error right here. This is the standard error already calculated for us right here. And was it 2.228 we got from the applet? 2.228. So this is 2.228 times 7.52856. And then this is the plus or minus, and the y bar is 131.545. And let's go ahead and solve just one of these here to show it can be solved this way. This is really good practice if you want to go the extra mile on this, which is not a bad idea at all. We're solving for the margin of error right now. 5682. And that's the margin of error. So we're going to add that right here to the center of the interval, and 54545. And that's 148 point. You see it rounds. They're carrying some more decimals that we're not carrying, but notice how we got this, and we can subtract minus the margin of error, and we get that right there. So you notice you're getting literally almost decimal place accurate to their answers. It's because the t-statistic is a little more finely calculated. If you really want to go crazy, last thing right here, it's going to be QT, is it? 10 degrees of freedom, 0.025, is that right? No, it's PT. And no. Is it not QT? NA is produced? What? Oh, let's check my code later. No degrees of freedom. Oh, is the degrees of freedom first? There we go. That's the correct T statistic. 2.228139. So there's a 139 after this. So how would you solve for the S since it's not given? On the test, we wouldn't do that. Great question right there. On the test, we wouldn't have you solving for that. So on the test, we wouldn't expect you to solve for the standard deviation. We'd have to give it to you. Standard deviation's a not fun problem to solve. It's more work than you want to do by hand. And then if it's required. So we might give you the standard error. We could give you the standard deviation in the output. So knowing that this is S, let's mark this really quick right here. Knowing this output is important. This is output you could get on the test, and you would have to know this is the standard deviation, this is the standard error, this is the Y bar, and yeah, this is the sample size, and degrees of freedom are going to be n-1, and that's going to be 10. Probably the most, does that make sense, Lakeisha, right here? This is important to know. I can solve this problem by hand, which is why I'm asking my jump crashed. Oh, okay, yeah. You can only solve this problem by hand. If you're trying to solve it by hand, do you have a TI calculator that can actually do it? Can you? Yeah, of course. Oh yeah, 100%. 100%. I should be able to get to it. I get to all the emails a little bit later. I take a break, eat some dinner, and then I definitely know 100% definitely. You got it. You should be able to. Let me bring this up right here. I think Google can do it too. Let's try Google. Calculate. Let's go to Google. I'm gonna Google. Okay. Standard. Here's calculator.org. So you'll see in a second here. I don't like putting in random websites. Can Google not really tell us the standard deviation? There should be a lot of online sites. If I'm going to put out a link, I'd want to make sure. But if you're calculating standard deviation, there should be standard deviation calculators. Just random sites are kind of iffy. I'm not going to send out a random site. Khan Academy. I trust Khan Academy. Do they not have a calculator for standard deviation? Let's try this. Watch the magic trick. Ready? We're currently using Wolfram. Oh yeah, Wolfram Alpha. What? Wolfram Alpha. Wolfram Alpha, of course. Standard deviation of. Probably is it gonna correct my typo? Interpret it as nice. And so it's telling me this is the standard deviation, and we could check the work right here. So let's go check that work and see if it is correct. So standard deviation of concatenated vector, this unexpected. My brain is slowing down today. There we go, 2.07. And Wolfram Alpha reports. Wolfram Alpha, great site right here. So it reports the same thing. Awesome. See you in a little bit, ditto. So Wolfram Alpha, a great way if you want to put in, and you can just ask the questions. Might even be able to use microphone and stuff, but really good stuff right here, Lakeisha, to use if you're solving it by hand. You could frankly, here's the scary thing. Let me try something because we're at the end of this problem. Copy to clipboard. I wonder if Wolfram Alpha just does this. Oh, no, no. It's... No, no, no. Well, that's a bummer. I thought Wolfram Alpha would actually do this. I am shocked it can't just flat do this. Let's see what it does. Can it just straight solve your math problem? I'm highly interested if it just solves it. Oh my gosh, I think it's... It might have... It's doing a crazy formula. What's it doing? 9.86 to 10 point... What did it do to our numbers? Sample size 130. Nah. Not doing it. A little bit of fun here at the end as we work on this problem. So jump will get you the numbers. So jump is getting us the upper and the lower number right here. So we have here 148.32. I literally thought Wolfram Alpha could just do it. And so when we do this, the confidence interval, they're saying 130 is their claim. Yeah, I believe that. The confidence interval contains its claim of 130, so this claim is supported. Awesome work. Do we have one more? Might head off here in a second. But Lakeisha, how's it going? Doing pretty well on this? Good review. Put a little music on. I'm surprised Wolfram Alpha doesn't just solve it. How do you find when you have a problem that has confidence interval of the mu? So which one is that you're working on right there, Jake? If you're working on one that says a confidence interval for mu, I think we'll find that one real quick. Here, let's take a look. There's one that talks about the mu, and I think it's trying to do... Are you talking about this right here? So when we do this right here, this one's trying to estimate the true mean. Oh no! Are you trying to find the standard deviation? Do you have a TI calculator? There should be standard deviation calculators. Put inside your interval right here. Standard deviation of... And then put this in here. So this will find you the standard deviation. So this should find standard deviation. It found it a moment ago. It's literally only interpreting the first few L's. That's insane. Maybe we should not put it in a parentheses. Let's take a look at the next problem here. The pulse one? Awesome. Let's take a look here. I don't know why it's not interpreting the full thing. Yeah, Lakeisha, email me if you can't find it. But you'll want to find the standard deviation, and standard deviation can be calculated online, all that good stuff. Explain carefully what this output means right here. We have right here, how do I do it on the calculator? So this one wants us to calculate the margin of error, right? So with this one right here, are you talking about this one right here? Calculate the margin of error? What is the margin of error? How do we find the margin of error? So remember, if I tell you tonight, the test will be between 6 to 7. Sometime that point tonight, the test will be between 6 to 7. So then how would we calculate the margin of error? Whenever you hear margin of error, what do you think of visually? The margin of error is what? So if you hear the margin of error and you hear 6 to 7, the margin of error is always what the length of the interval. So whenever we hear the margin of error, we always think this the length of the interval. Let's draw a little bit of what it'll look like right here. And let's think about what the margin of error is. So we have an interval, and then we have a margin of error. So the margin of error is always what the length of the interval. If we have a margin of error, like I say, at some point between 6 and 7. Sherry, great job. Sherry, 100 points right there. Sherry, rock star. Got it. So the margin of error is always... Great job, Andrew, right there. Also, nice points. You get it. Awesome work. The margin of error is going to be plus 30 minutes, minus 30 minutes. So conceptually, we should remember the margin of error... Nice job, Jake. Awesome work. 100 points there, Jake. We should remember the margin of error is half the length of the interval. So the margin of error being half the length of the interval, we want to take the upper portion of the interval minus the lower. So here's the upper. Enough decimals right there. Minus the lower. And divide by 2. And that's half the length of the interval. So that's going to be 2.4. And now explain carefully what this output means. I am 95% confident the true pulse rate of these individuals is contained in the interval. Go for the finding the critical... Yeah, that's one of my favorite questions. Let's do that one. We got just enough time. Teaching class in 14 minutes. I'll send an announcement out here, but we got just enough time. No, grab a snack. If they did a 90%, what do you think here? They did a 95, and if we did a 90, it's going to be smaller. Remember, 95, 90, 68, 95, 99.7. If 90, it's going to be smaller. So the margin of error would be smaller. One of my favorite questions right here, Juliet, is those t-distribution questions. I think it's like number 7. We're gonna hop back into this in a moment right here. Let me clear the screen, and we'll jump back into this. Turn on. Is this one just playing? Awesome. What about finding the constant interval when it gives mean and standard deviation with n? We did some of those earlier. We got time for early. One more question right here, because teaching 12 minutes. I'm gonna send the announcement out to class that their class is about to start. But check out the earlier office hours, and let me send the announcement to them. We're gonna do some critical values here to end. I'm sending the class announcement to time series right now, saying your class is beginning here in 12 minutes. Then snack time between class. 12 minutes. We got this. Class, 12 minutes. Big bonus. See you soon. No caps. Click here. Okay. Sending announcement to class. Announcement being sent. And you're welcome, Jake. Anytime, man. Anytime. We have them. Check out the earlier videos. Yesterday's videos are marked. All the videos for this week are marked except for the morning video. So check it out. You'll see a lot of the problems us working through, like the hot dog question, the yogurt question, the 1,000-chip trial question, the golf club question, the airlines question. You might be working on one of those, like golf club or airline. That sounds like a golf club or airline question. So go check out. You'll see it marked golf club or airline question, and you'll get it. Awesome work. One of my favorite questions here, though, is find these t critical values. Just a short one, too. So let's go check it out. Andrew's already there. Good to have you here, Andrew. So with this right here, we are building t intervals, and we need the critical value. What we need to know, though, is that we have to go to a t-applet to get these values. You can kind of guess them if you've been doing this a while. So let's see right here. 2.08. 2.64. There you go. Done. Let's show how it's done. Now, the reason I'm able to guess these is because some of them are closer to the Z statistic. The Z statistic for a 95% confidence interval is 1.96. But the T and the Z are different. The T is not the Z, but the T will become the Z with a lot of degrees of freedom. So when you... Let's decrease font over here. This T has with it 23 degrees of freedom. We have to put 23 degrees of freedom in, and I was close enough with my guess to get it correct. Because I knew it's 1.96 if it's the Z. So I was like, okay, remember the T, Mr. T flattens it out, smashes it down, and we see that it is further smashed down. It's behind me right now, the 2.07, which I was close enough with my guess. So now we go to a 99% confidence interval. And with the 99% confidence interval, we have 61 degrees of freedom, but I know the answer to a Z-score is 2.5758. But with 61 degrees of freedom, it's a little more smashed down. I got very lucky it gave me that one. Well, because I know the Z-scores, and that's how I'm able to get these a lot of times. I can guess them because I know the Z-score. Okay, like, wait, Andrew, you got this one. Andrew, remember 1.96? Smash it down. The degrees of freedom will be... So good question right there, Jake. The degrees of freedom for a one sample T are the formula n-1. We got that on here somewhere. n-1 are the degrees of freedom. So that means this problem came from a sample size of 108. This problem came from a sample size of 8 because the degrees of freedom are n-1. So the sample size here was 108. It didn't tell us the sample size, but if it did, it might say the sample size was 108. Then we know the degrees of freedom are 107. For the one sample T, it's n-1. So think about this, though. The Z-score here is 1.96. So if it's only smashed down a tiny, tiny bit, what might you guess as the T-score? A tiny, tiny bit. Andrew, I bet you can get this one. You got this, man. What do you think the T-score would be here? It's only very tiny, tiny bit. Very little smash down. Very, very little. Very little. Little tiny bit.
Tiny bit. Little bit.
Only a little bit. Tiny little bit smashed. Little bit. Oh, way too smashed. Way too Hulk smash. Tiny, tiny bit. Tiny, tiny bit. This one has a lot of freedom. It's very little smash down. This one is very smashed down though. This one is very hard to guess. If I get this, amazing day. That's very hard to guess. Yeah, that top one is very smashed. 7 degrees of freedom with 99% confidence is a T-score of 3.5. I'm actually shocked I'm that close to it. That was a bad guess, but much closer than I thought I would get. But this is just barely different from 1.96 because the Z-score is 1.96 for 95% confidence, and then it's just barely different because after about 100 degrees of freedom, they're virtually identical. So the T and the Z converge towards the same number as T goes towards infinite degrees of freedom. Like if I ask you a 90% confidence interval with a ton of degrees of freedom, like 600 degrees of freedom, and if I put in 90% confidence, it's going to say 1.6545, 1.645. I thought I was going to round it up, but 1.645 right there. If I put in 80% confidence, it's going to be 1.282. I should put 2 on there. But these are Z-scores now. But if you bring down the degrees of freedom, the numbers are going to start to change, and the T curve is going to be more smashed down. So anytime, last thing to say right here, anytime you talk about a T, you must ask someone, what are the degrees of freedom? And for the one sample T, those degrees of freedom are, last but not least, the formula n-1 for degrees of freedom. Well, that's got it. We'll be back here tomorrow with more office hours. Thank you, everyone, so much. n-1 for those degrees of freedom. I'll see you in time series pretty soon. See you, Andrew. Gonna go grab a snack. Bye for now, everyone. Bye.